Good morning. Welcome to our Red Short webinar for this Wednesday, May 31st, 2023. My name is Felicia Schenkelberg. I am an analyst here with Red Sky Alliance. Today I will be walking you through a short discussion on some recently released information on the effectiveness of information redundancies as a countermeasure against differential fault analysis, or DFA, attacks on the Advanced Encryption Standard. As always, you can find information on related topics at redskyalliance.org. The Advanced Encryption Standard, or AES, is a widely used block cipher in symmetric key cryptography. As you may well know, it was adopted by the National Institute of Standards and Technology in November of 2001 as the U.S. Federal Information Processing Standard. The AES cipher, based on the Rindell algorithm, was selected by NIST as a replacement for DES, or Data Encryption Standard cipher. Despite its widespread adoption, AES is susceptible to DFA attacks, which exploit the operating errors and compromise the security of the cipher. In this presentation, I will delve into the effectiveness of information redundancies as a countermeasure against DFA attacks on AES. So here's the agenda for today. We will begin by covering both AES and DFA. Next, I'll move on to explore the concept of information redundancy, specifically focusing on advanced fault detection schemes. And then these will be based on the signature generation using Hamming schemes. After that, I will discuss how this information highlights the need for continued research and development in the field of cryptographic systems, specifically addressing the vulnerabilities in the AES to differential fault analysis attacks. And then lastly, I will note how the findings in this research emphasize the importance of implementing effective countermeasures to protect AES implementations from potential security breaches. So let's get started. All right, so AES supports different key sizes. And these are 128, 192, and 256 bits. All of these determine the level of security provided. So the higher the number, the more security. The encryption process of AES involves multiple rounds, with the number of rounds depending on this given key size chosen. So it would be 10 rounds for a 128-bit key, 12 rounds for a 192, and then 14 rounds for a 256. So each one of these rounds applies a set of transformations to the input block, and then this input block is typically referred to as state S. So this is like your input, your starting state. The round process in AES consists of several operations. Each one of these, there's 4 typical ones. There's byte substitution, row shifting, column mixing, and then an additional round key. So these operations collectively transform the state S, which is your input, so your plain text, to produce the encrypted output. DFA has become one of the main methods for compromising the security of block ciphers that's widely used in a multitude of environments and applications due to their great effectiveness and the real threat that they pose to the security of cryptographic devices and therefore the integrity of your user data. The scientific community has turned to proposing different mechanisms for detecting this type of attack. Each of these mechanisms has a significant cost or does not adequately prevent cipher implementations against numerous DFA models. So these countermeasures or detection schemes try to minimize the vulnerabilities of crypto circuits against different attack techniques. So there are therefore numerous proposals for detection schemes reported in the literature, such as hardware redundancies, temporal redundancies, information redundancies, and then a combination between these. But as mentioned previously, we will be discussing primarily the effectiveness of information redundancies as a countermeasure against DFA. So information redundancy refers to the incorporation of additional redundant data to the encryption or decryption process of the system. So the purpose of introducing these redundancies is to enhance the fault detection capabilities of the system and to detect the identity of any potential faults or errors that may have been injected during the cryptographic operations. So you can kind of think of this as like a hash that you would append to the end of a message. So this would be similar to a signature scheme. In the context of differential fault analysis, DFA attacks on AES, information redundancy aims to provide an extra layer of protection by including this supplementary information to the data being processed. The information redundancy here works by providing additional information. As mentioned before, this extra information, which can be bits, allow the user to identify if faults were injected during the process. This is done by comparing the input to what's the output afterwards. So like if it's encrypted and then it's decrypted and then these bits don't match, then you know that something went wrong with the encryption or decryption process. Differential fault analysis, or DFA, attacks work when an attacker tries to manipulate the circuit with the possibility of using different degrees of invasion. This is being more or less aggressive with the device. This is the most popular type of attack because it is both cheap and allows the device to be manipulated without leaving a trace or without causing permanent damage. In this case, the attacker can generate transient operating faults or errors and then obtain the secret information contained in the device. These types of faults combined with different mathematical formulas can be used to retrieve the secret information. So that's just DFA in a nutshell. Okay, so the concept of information redundancy specifically focused on advancing or advanced fault detection schemes, utilizing Hamming schemes, highlights the potential for improving the reliability and integrity of cryptographic systems. And these are by generating signatures that enable effective fault detection. Hamming codes are well known as a family of linear error detecting codes. And this was, of course, invented by Richard W. Hamming in 1950. The main use of these codes is to detect faults in the data transmission and correct them. These codes utilize additional bits, variety bits, to create a signature or code that can detect errors. By adding redundancy in the form of bits, the system gains the ability to identify inconsistencies or deviations from the expected data patterns. In the context of fault detection, Hamming schemes are employed to generate signatures that can be used to identify and detect potential faults or errors. And then these schemes involve the incorporation of Hamming codes as a signature generator, and these signature generators generate the signature. The process begins by generating a signature using Hamming codes, and then these signatures are based on the data being encrypted or decrypted. And then these bits are appended to the data, creating the signature, which is the expected pattern. During the cryptographic operation, if any faults or errors are detected which alter the data, the signature generated will no longer match the received data. This discrepancy serves as an indication of a potential fault or error in the system. So by advancing fault detection schemes based on signature generation, recent research published by a few different researchers found that given an experimental attack set up designed to evaluate the fault coverage of each scheme, that the Hamming scheme in particular offered 100% protection. But it is important to note that the effectiveness of information redundancy and fault detection schemes based on Hamming codes depends on various factors such as the specific implementation, the size of the data being processed, and then the chosen error correcting capabilities of the Hamming codes. So rigorous evaluation and analysis are always necessary to ensure that the redundancy and fault detection mechanisms provided by these schemes are robust and effective enough to detect a wide range of potential faults and errors in the cryptographic system. So in the research attached to this report, the results demonstrated that all the countermeasures had a resource overhead of less than 42%, with the priority scheme exhibiting a particularly low overhead of 9%. What this means, like the overhead, means that the countermeasures can significantly impact the overall efficiency and practicality of implementing such schemes. So the resource consumption analysis reveals that the proposed fault detection schemes based on information redundancies in AES have a resource overhead of less than 42%. So this indicates that computational and memory requirements are within acceptable limits for practical deployment. Frequency degradation is a crucial factor to consider when implementing countermeasures. It's essential to ensure that the proposed scheme does not result in a noticeable slowdown of cryptographic operations. And their evaluation results indicate that none of the proposed schemes impose a frequency penalty compared to the unprotected cipher. This signifies that the fault detection mechanisms based on information redundancy can seamlessly integrate into AES without compromising the operational speed. So by utilizing advanced fault detection schemes, specifically based on the Hamming signatures, we can enhance the security and integrity of AES implementations. Future work can explore the integration of these schemes with other cryptographic algorithms and evaluate their effectiveness in real-world scenarios. The pursuit of stronger security measures is essential to ensure the confidentiality and integrity of. So let's recap. In summary, we discussed the effectiveness of fault detection schemes in enhancing the security and integrity of AES implementations. Future work can explore integrating these schemes into other cryptographic algorithms and assess their effectiveness in real-world scenarios. And it's crucial to continuously pursue stronger security measures to safeguard the integrity and confidentiality of sensitive information. Thank you for joining us. I hope you enjoyed the material and found it useful. If you have any further questions on the subject, you can contact us via Jim McKee at jimmckee@wpaclabs.com. Have a nice day, and we hope to see you again next week.